Whether it's melting ice sheets stranding polar bears, droughts decimating crops, or unrelenting storms flooding entire cities, it's clear that our planet is facing a host of alarming changes. Scientists view these changes as part of a larger trend in global climate. How has Earth's climate changed over time? And what's in store for our planet in the future? Dr. Jim Hack, the director of the National Center for Computational Sciences at Oak Ridge National Laboratory, is one of the scientists trying to answer these questions.
So we most often hear about climate change in the context of how much the planet's going to warm by the end of the 21st century. And that's useful information to know that there's a trend there, but it's not necessarily actionable information if somebody needs to be able to respond to the consequences of climate change, right?
In this expedition, your goal is to investigate the causes and impacts of climate change and learn how scientists are working to predict Earth's climate future. To accomplish your expedition goal successfully, you'll need to discuss natural factors that cause climate change, describe ways in which humans have accelerated global warming, explain how scientists construct and use computer climate models. Climate change is any significant change in the statistical measures of the climate system that lasts for an extended period of time. And a climate model is a mathematical model that represents the complex interactions of Earth's atmosphere, ocean, land surface, and ice, and which attempts to predict climate change. Climate models are based on current climate information collected by weather stations, satellites, and drifting buoys. They also incorporate historical climate records derived from things like ice cores and tree rings. Once Hack and his team develop a model, they run it on some of the world's fastest computers, like Titan and Kraken. And these extreme number crunchers live up to their epic names as they run the climate models over and over to predict our future climate.
That's what these computers are for. They're here to help us manage these large volumes of data, and not only manage the data, but export the data, make it discoverable to people on the outside, so others can engage in the process of understanding and managing the consequences of climate change.
Once the supercomputers run the climate models, the results are visualized on a state-of-the-art screen called Everest.
This is actually a simulation. So what you've done is written down all the equations that govern the fluid motions, and then you throw the switch, and that's what will be produced. If you've got a good idea of what those equations are, you can produce something that looks pretty much like the real world.
Yeah. These simulations can show weather and climate and help scientists understand the relationship between the two.
There's a linkage between weather and climate. Climate is the long-term statistical characterization of weather. So everything that happens outside in the way of weather events, the storms that come through, the nice, clear, sunny days that come by, all those things are averaged up in some way to determine aspects of climate.
For Hack and other climate scientists to be able to create climate models, they must understand and account for all of the influences on climate. The major factor behind weather and climate that must be considered for the models is the sun.
Well, the sun's the source of all the energy for the climate system. So that's the thing that's fueling weather on the planet, and it's the weather events, the phenomenology of weather, that determines what our climate looks like in any place on the Earth.
Earth absorbs energy from the sun and then reflects and re-radiates some of the energy back out into space. It's a constant balancing act and a critical factor in making our planet's climate livable.
With any kind of system, a closed system, you have a budget. What comes in typically equals what goes out if the system is stable. So in this case, we have the Earth intercepting energy from the sun, and the energy that's intercepted from the sun is absorbed by the system. Then that system re-emits energy at its own temperatures, and whatever escapes the system through energy at the top of the atmosphere is the other part of the equation.
Another big factor in the equation? Water, in the form of clouds.
Representing low clouds over the ocean is really important to do the problem correctly. They reflect sunlight because they're low and they're liquid water clouds. And the liquid water clouds tend to have the strongest impact on the solar radiation budget. So if you have more clouds, they tend to cool the planet. And if you have fewer clouds, they tend to have a warming effect on the planet. The other uncertainty has to do with high clouds, and these are dominantly ice clouds. So when you're flying in the airplane back home and you're looking out the window, most of those clouds, once you're at altitude, they're ice clouds, completely ice. And they have a dominant effect of trapping radiation and warming the planet.
Water affects the system's energy budget in another way, too. Ice, in the form of glaciers, also plays an important role in the climate equation.
Can anybody give me an idea of why changes in glaciers would be important?
Since glaciers are white when the sun shines on them, they reflect probably a lot of that radiation back up into the atmosphere.
Right, and that's what we were talking about when we talked about albedo. Albedo is just how bright the surface is.
As the planet warms and glaciers melt and disappear, it changes not only the regulation of Earth's energy budget, but also the lives of people living near the glaciers and along coastlines where sea level is rising.
So what we want to try and show in this animation is the fact that there are plenty of places in the world that are vulnerable to climate change. Why we care? Why does it matter? A very major source of the water for people in this part of the world are the glaciers that exist in the Himalayas. And so if you looked at this problem and said, let's take the glaciers out, or they don't exist, the river systems that exist that provide fresh water for all these people would become seasonal rivers. That is, they'd go dry at some part of the year. And so this is an example where the impact of climate change on melting away these glaciers would have huge impacts downstream because all these people would have serious problems with access to water supply.
One well-documented change in climate is global warming, a steady rise in Earth's average temperature over time. Scientists have linked these higher temperatures to greenhouse gases such as carbon dioxide and methane.
So why are they called greenhouse gases?
And think about your greenhouse that you assemble in the middle of winter. It's clear to the outside, and solar energy can come in very efficiently. But when it hits the surface in there and warms that surface, it re-radiates the energy at longer wavelengths, but those wavelengths tend to be trapped inside the greenhouse. And that's why greenhouses work.
While the greenhouse effect is a natural process that maintains Earth's livable temperature, too many greenhouse gases in our atmosphere limit how much of the sun's energy can escape back out to space. This is heating Earth at an unprecedented level. So where did this spike in greenhouse emissions come from? The short answer: humans. We burn carbon dioxide emitting fossil fuels to power our cars and warm our homes. We've cut down trees that remove carbon dioxide from the air through photosynthesis. And we've raised hundreds of millions of cattle that release methane every time they burp. These and other human-driven behaviors are clearly altering our planet. Greenhouse gas emissions are an extremely important piece of the climate model puzzle. Understanding the many different sources of greenhouse gases and how they will respond to our changing climate is critical. Scientists like Dr. Paul Hansen are trying to better understand these processes by replicating climate-sensitive environments and artificially warming them. They want to see if the higher temperatures will release greenhouse gases stored within an environment's soil, such as those trapped in a northern forest floor or in permafrost. This knowledge will help scientists revise their computer models to more accurately predict the rate of future change.
The enclosure in the spruce lab was there to artificially create a warmer environment for a little space of ground, and they wanted to do that so that they could figure out if that warmer climate will affect what gases are coming out of the ground. That's really important for them to figure out, just in case, global warming takes a turn for the worse.
Using some of the world's most advanced technology, scientists are working hard to figure out what our future climate may look like. What we do with that information is up to us.
So how do you guys think you might act on what you've learned during this visit? What do you think you might do with that information when you go back home?
I learned how to analyze complex graphs. There's math behind everything that we do in this world, and we can use supercomputers and other technologies to get a better understanding of what's around us and an easier way to see it.
Be good stewards of the environment that we live in. It's an easy thing to do. So thanks for coming.
Yeah, thanks.
Thank you.
Yeah.